Welcome to The Explainer. Today, we're stepping right into the cockpit to explore a high-stakes, hyper-technical, and honestly a surprisingly fascinating world, and that is aviation weather reporting. You know, every single time you board a commercial flight, there's this incredibly complex, massive web of data working completely silently in the background just to make sure you reach your destination safely. And the crazy part? It is entirely invisible to the naked eye. Picture this for a second. You're cruising along at 35,000 feet. You're sipping a ginger ale, and out of nowhere, the seatbelt sign dings on. How exactly does your pilot know that a massive thunderstorm is brewing 500 miles away on your flight path long before they could ever actually see it? I mean, how do they know the exact temperature of the air outside or the precise condition of the runway they're going to land on in 3 hours? Well, today we're going to decode the secret language of the skies. Section 1. The Global Weather Web. Okay, let's dive right into this. To understand how your specific flight navigates the weather, we really have to start at the very top. At the macro level, it all begins with the UN. Their specialized agency, the World Meteorological Organization, acts as the ultimate authoritative voice on the Earth's atmosphere. They set the strict accuracy standards for aviation weather. Then, those standards are actually put into practice globally by two main World Area Forecast Centers, or WAFCs for short. One is operated by the US in Kansas, which is known as the Washington Center, and the other is run by the UK in Exeter, and that's referred to as the London Center. Now, what's really interesting here is the sheer contrast between old-school meteorology and what these centers actually do. The source materials detail these very gritty, handwritten notes, but what they describe is a hyper-advanced, mind-bogglingly complex digital reality. These two WAFC centers produce what's called Numerical Weather Prediction. Basically, they build massive mathematical models of the atmosphere and oceans, creating this immense 3D grid of weather data. We're talking horizontal data with latitude and longitude, combined with vertical data mapping altitude and pressure. And why this matters so much is because this massive mathematical grid forms the absolute bedrock of every single decision a pilot makes. Moving right along to Part 2, Weather's Alphabet Soup. So, the global grid exists, but how does that massive amount of data actually get communicated to a pilot sitting on the tarmac? Well, the crucial point is understanding the difference between the two main types of reports pilots review. First up, you have a MEDAR. A MEDAR is the actual current weather at an airfield, recorded at specific synoptic hours. It's exactly what is happening right now. Contrast that with a TAF, which stands for Terminal Aerodrome Forecast. A TAF is just that. It's a forecast. It's inherently a lot more vague, and it always comes with a specific forecast time and period of validity. Pilots absolutely rely on checking those specific times to know if they need to extrapolate forward to predict what the weather will be by the time their route reaches that airspace. But here's the catch. These reports don't read like a normal weather app. The conditions are shrunken down into tight little cryptic codes. Let's play a rapid-fire game of translation. If a pilot sees TS on their briefing, they know a thunderstorm is ahead. GR, that means hail. SEV-TURB is exactly what it sounds like, severe turbulence. SEV-ICE, FCRA, warns of severe ice from freezing rain. And TCU, that points to towering cumulus clouds. Decoding this really feels like cracking an insider language. And for pilots, fluency in this exact code is literally a matter of life and death when they're navigating a crowded sky.
All right, Section 3, Plotting the Pre-Flight Route.
Now that we know the language of the sky, we need to talk about how pilots actually map it out. Before takeoff, they don't just look straight ahead, they have to look up. The International Civil Aviation Organization, or ICAO, recognizes three main weather domains stacked on top of each other, sort of like a towering, invisible layer cake. You've got the low level, stretching from the surface up to flight level 100, then the medium level, from flight level 100 up to 250, and finally the high level, soaring all the way from flight level 250 up to a staggering flight level 630. This structure is totally essential because the atmosphere behaves entirely differently depending on which slice of the cake your plane happens to be flying through. So when prepping for a flight, pilots use meteorological charts to see exactly what's happening inside those specific layers. They're checking a massive checklist: upper air winds, temperatures, humidity, and SIGMETs, or significant weather phenomena. They even check the flight level and temperature of the tropopause, which is the boundary layer between the troposphere and the stratosphere. It isn't just a list of numbers, it's a living, breathing, three-dimensional map that tells the flight crew exactly where the ride will be smooth and where they might need to alter their route just to keep you comfortable in the back. Part 4. In-flight high-tech updates. Let's see how this builds once the aircraft actually pushes back from the gate.
Because pre-flight briefings are fantastic, but weather is incredibly dynamic. What happens when a plane is moving at 500 miles per hour and needs real-time updates? This is where the in-flight tech gets absolutely amazing. Aircraft can receive text-based meteorological info via the AFTN, which is the Aeronautical Fixed Telecommunication Network. But a really vital tool here is ACARS. ACARS is a direct ground-to-air data link that blasts critical information, warnings, and significant weather alerts straight into the cockpit computers in real time. It's an invisible lifeline. Even if a storm pops up suddenly out of nowhere, the ground stations can beam that warning up to a jet flying miles above the Earth in a matter of seconds.
Section 5, the Bristol Foxtrot example. To see exactly what that real-time localized data looks like just before a plane lands, let's look at a hyperlocal, real-world example from a UK airport. This brilliantly illustrates the final stage of the weather journey, the ATS, or Auto Terminal Info System. Imagine an automated voice rapidly looping this over the radio right as you're preparing to land. It sounds a bit like, Bristol, information Foxtrot, runway in use 09, left hand, prevailing visibility 2,000 meters, light rain, runway, wet, 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 fog warning current. Now that rapid-fire wet, wet, wet isn't a glitch in the audio. It's specific insider code, meaning the beginning, middle, and end sectors of the runway are all currently flick. And that fog warning, that tells the crew visibility is dropping rapidly below 600 meters. This ATIS information is a highly dense broadcast that's reviewed and updated every 30 minutes, or absolutely any time a major weather change warrants it. It gives the pilot the exact, actual conditions of the traffic, the weather, and the runway surface they're about to touch down on. It is the absolute final localized guide for a safe landing, making sure the crew has zero surprises as they descend through the clouds. Which brings us to Section 6, planes as weather stations. And honestly, this is the coolest plot twist of the whole system. We've talked all about how planes consume this weather data to stay safe, but they don't just consume it, they actually create it. That's right, commercial aircraft act as high-speed flying weather stations. Meteorological authorities actually require aircraft to report on the weather they observe. They do this through routine airpaps, reporting their position, flight level, temperature, and wind. If they hit severe turbulence or hail, they issue an immediate special airpap. Even more amazing is AMDAR. This is automated software on the aircraft that records data during the climb, cruise, and descent, and then transmits it via satellite link straight back to those World Area Forecast Centers we talked about earlier. So every single flight you take is actively feeding and improving that global 3D grid for the plane right behind you. How cool is that? Yet despite all this incredible high-speed automated tech and satellite uplinking, some of the most crucial data still comes from something delightfully old school, and that's weather balloons. Radiosonde observations involve collecting upper air data by launching a physical balloon into the sky. It measures temperature, pressure, and humidity. It radios that data back to a ground station and uses ground radar tracking to determine upper wind speeds. It's just such a beautiful, surprisingly simple mix of classic meteorology and modern aviation tech working hand in hand. So, the next time you board a plane, settle into your seat and gaze out the window at the clouds, ask yourself this. Will you just see a blue sky? Or will you see the invisible 3D web of data, the automated reporting software, the weather balloons, and the constant global communication loop that is tirelessly working to keep you airborne and perfectly safe? It's a remarkable system, and now you know exactly how to decode it. Thanks for joining me on this explainer, and I will catch you on the next one.